Professor Belfrost's computer science class is back!
Okay, so welcome back to my channel. Today you are joining my class again on Monday, and I will continue my previous lesson. Now we will start discussing about processor, CPU. Okay, so this is the fifth episode about computers component, right? Okay, so let's review our last lesson. So there are basically three I/O operation techniques: program I/O, where there are exchanges between the processor and the I/O module. This processor executes a program that gives it direct control of the I/O operation. And when the processor issues a command to the I/O module, it must wait until the I/O operation is complete. There are four types of I/O commands. We know control, test, read, and write. And also there are two modes of addressing, which is called memory map addressing mode and isolated addressing mode. Okay, so the second one is interrupt driven I/O, where processor issues an I/O command, continues to execute other instructions, and is interrupted by the I/O module when the latter has completed its work. So there are four approaches to address design issues of these techniques, called namely multiple interrupt lines, software poll, daisy chain or hardware poll factor, bus arbitration factor. Okay. The third type is direct memory access (DMA), where I/O module and main memory exchange data directly without the involvement of processor. Okay, so there are three DMA mechanisms exist. The first architecture is single bus detached DMA. Second is single bus integrated DMA I/O, and the third one is I/O bus. And there are two types of I/O channels, which is selector and multiplier. That's done. That's the recap from our last lesson. Now we are moving start to covering processor. Okay, so CPU process very important. So this is the brain of computer, and the processor actually just consists of registers, the LLU, the instruction execution unit, the control unit, and the intersect interconnections. I mean, among these components. Actually, at first, I want to give you lecture on ALU first because actually that should be the order, but I haven't prepared the material really good. I mean that I'm still collecting many ALU materials so that I can give you better lecture there. So I'll explain from control unit. Okay. Okay, so control unit is one part of the processor, and this is the portion that actually causes things to happen. The control unit uses control signals external to the processor to cause data exchange with memory and I/O modules. So the control unit also issues control signals internal to the processor to move data between registers to cause the LU to perform specified function to regulate other internal operations. Input to the control unit consists of the instruction register, flag, and control signal from external sources like interrupt signals. Yeah, for example. Okay, so we have seen that the operation of a computer in executing a program consists of a sequence of instruction cycles with one machine instruction per cycle. Of course, we must remember that this sequence of instruction cycles is not necessarily the same as a written sequence of instructions that make up the program because of the existence of what called branching instructions. And what we are referring to here is that the execution time sequence of instructions. We have already seen that each instruction cycle is made out of a number of smaller units. Okay, one subdivision that we found convenient, yeah, is fetch, indirect, execute, and interrupt, with only fetch and execute cycles always occurring each time. So to design a control unit, however, we need to break down the description further. We'll see that each of the small cycles involves a series of steps, each of which involves the processor registers. And we will refer to these steps as micro operations, new terminologies for you. Okay, so the prefix micro here refers to the fact that each step is very simple and comprises very little. So, you'll be given a figure on the next slide, and it depicts the relationship among the various concepts that we have been discussing so far. To summarize, the execution of a program consists of the sequential execution of instructions. Each instruction is executed during an instruction cycle made up of certain subcycles called fetch, indirect, execute, and interrupt. And the execution of each subcycle involves one or more certain operation, which is called micro operations. Let's see. This is the figure. You may take a screenshot if necessary. Okay, so yeah, micro operations are functional or atomic operation of a processor. So as what I've stated before, there are some of these. First one is fetch, fetch cycle. Fetch cycle occurs at the beginning of each instruction cycle and causes an instruction to be fetched from memory. And there are four registers that are involved in this cycle: MAR, MBR, PC, and IR. What it stands for? MAR. MAR, Memory Address Register. So it is connected to the address lines of the system bus. It specifies the address in memory for a read or write operation. Second, Memory Buffer Register, or MBR for short. It is connected to the data lines of the system bus, and it contains a value to be stored in memory or the last value read from memory. Third is program counter (PC), which holds the address of the next instruction to be fetched. The fourth is instruction register. This is the register that holds the last instruction fetch. Okay, to understand the sequence of events for fetch cycle, let's learn it by this simple example. Maybe it's necessary for you to take a screenshot first and follow up the explanation. Okay. At the beginning, as you can see from the picture given of a fetch cycle, the address of the next instruction to be executed is in the program counter (PC). In this case, you can see the address is 11001000. Okay. The first step is to move that address to the memory address register because this is the only register connected to the address lines of the system bus. Then the second step is to bring in the instruction. The desired address in the memory address register is placed on the address bus. The control unit issues a read command on the control bus, and the result appears on the data bus and is copied into the memory buffer register. We also need to notice that we need to increment the PC by the instruction length to get ready for the next instruction. Because these two actions, read root from memory and increment PC, do not interfere with each other, then we can do them simultaneously to save time. The third step is to move the contents of the MBR to the instruction register, and this will free up the MBR for use during a possible indirect cycle. Okay, thus the simple fetch cycle actually consists of 3 steps and 4 micro operations. Each micro operation involves the movement of data into or out of a register so long as these movements do not interfere with one another. Several of them can take place simultaneously, saving time. Symbolically, we can write the sequence of events that I've just described as follows. This is the, I can call this a pseudocode. Okay, so you can take a screenshot and try to understand by yourself. Where in this pseudocode, I represent the instruction line. Okay, we need to make several comments about this sequence. Okay, first we assume that a clock is available for timing purposes, and that it emits regularly spaced clock pulses. Each clock pulse defines a time unit. Thus, all time units are of equal duration. Each microoperation can be performed within the time of a single time unit. The notation given T1, T2, T3 in the picture represents successive time units. In words, we have first time unit, move contents of PC to MR. Second time unit, move contents of memory location specified by MAR to MBR. Increment by the contents of the PC. And the third time unit, move contents of MBR to IR. This is the description of the previous given pseudocode. Okay, so when we are going in this lesson and maybe another lesson later, you'll have many figures like this pseudocode. As you can see, actually this is not pseudocode, but it represents how something works. Okay, as you have seen another one in this slide. Okay, I want you to give your explain later this picture with your own word, like what I have given you the example for the first picture. Okay, so note that the second and third microoperation both take place during the second time unit, and the third microoperation could have been grouped with the fourth without affecting the fetch operation. Okay, and here we are. So this is the picture. Good. So now the groupings of microoperation must follow two simple rules. Please keep in mind. First one, the proper sequence of events must be followed. First, must proceed because the memory rate operation make use of the address in the MAR. Second, conflicts must be avoided. One should not attempt to read to and write from the same register in one time unit because the result must be would be unpredictable. Okay, you can just imagine how chaotic if two process take uh, is taking time this is taking place at the same time. Okay, using the source of register, the register will confuse which one to be handled first. Okay, for example, the micro operations should not occur during the same time unit. I mean the micro operation of the ones that using the same resource. Okay, final point worth noting is that one of the micro operation involves an addition. So to avoid duplication of circuitry, this addition could be performed by the LU, and the use of the LU may involve additional micro operations depending on the functionality of the LU and the organization of the processor. Okay, okay, done for the first cycle. The next is indirect cycle. Once an instruction is fetched, okay, then the next step is to fetch source operands. Continuing our simple example, let us assume one address instruction format with direct and indirect addressing allowed. If the instruction specifies an indirect address, then an indirect cycle must precede the execute cycle. Then the data flow includes the following microoperation shown, yeah, for the first, second, and third time unit. I want you to explain by yourself. So the address field of the instruction is transferred to the MAR. This is then used to fetch the address of the operand. Finally, the address field of the IR is updated from the MBR so that it can now contain a direct rather than indirect address. The IR is now in the same state as if indirect addressing had not been used and it is ready for the execute cycle. We can skip that cycle for a moment to consider the interrupt cycle. Okay, we are done with the second one temporarily. We'll back later. Okay, and now we discuss the second and the third one. Yeah, the third cycle, which is interrupt cycle. At the completion of the execute cycle, a test is made to determine whether any enable interrupts have occurred. If so, the interrupt cycle occurs. The nature of this cycle varies greatly from one machine to another. Here is the flow diagram. Okay, so it follows. In the first step, the contents of the PC are transferred to the MBR so that they can be saved for return from the interrupt. Then, the second time unit, the MAR is loaded with the address at which the content of the PC are to be saved, and the PC is loaded with the address of the start of the interrupt processing routine. And these two actions may to be a single micro operation. However, because most processors provide multiple types and or levels of interrupts, then it may take one or more additional microoperations to obtain the safe address and the return address before they can be transferred to the MAR and PC respectively. In any case, once this is done, the final step is to store the MBR, which contains the old value of the PC, into memory, and the process is now ready to begin the next instruction cycle. Now, we are done with the third one and move to the fourth, which is execute cycle. So the fetch, indirect, and interrupt cycles are simple and predictable. It involves a small fixed sequence of micro-operations, and in each case, the same micro-operations are repeated each time round. But now we are explaining about execute cycle. This is not true for execute cycle. Because of the variety of opcodes, there are a number of different sequences of microoperations that can occur. Let us consider several hypothetical examples. First example, consider an add instruction. This is the assembly language, add R1X. I will later dedicate some videos for explaining about assembly language, but don't worry for now. Even if you don't understand this code on assembly, you can still keeping this lesson with me. Okay. Okay, so this structure actually cause adding content of the location X to register R1. So the following sequence of microoperation might occur as shown in the flow diagram. Okay, we begin with the IR containing the add instruction. Then in the first step, the address portion of the IR is loaded into the MRR. Then the reference memory location is read. Finally, the contents of R1 and MBR are added by the ALU. Again, this is a simplified example. Additional microoperations may be required to extract the register reference from the IR and perhaps to stage the ALU inputs or output in some intermediate registers. Okay, now let us look at more complex example. Here I can give you the second example to this is a common instruction increment and skip if zero ISZ S. Okay, so content of location X is incremented by 1. If the result is 0, then the next instruction is skip. A possible sequence of micro operations for this case is as shown. Okay, so from the figure, we can figure out that the new feature introduced here is the conditional action. We have conditional action if. Okay, so the PC is incremented if MBR equals 0. And this test and action can be implemented as one micro operation. Note also that this micro operation can be performed during the same time unit during with the updated value in MBR stored back to memory. And finally, consider routine call instruction. As an example, consider branch and save address instruction BSAX. Yeah. So here's the picture. Okay, the flow diagram. Okay, so the address of the instruction that follows the BSA instruction is saved in location X and execution continues at location. Then the save address will later be used for return. And this is a straightforward technique for providing subroutine calls, and the following micro operations suffice. Okay, as have been shown before. Okay, so the address in the PC at the start of the instruction is the address of the next instruction sequence. This is saved at the address designated in the IR. The layer address is also incremented to provide the address of the instruction for the next instruction cycle. Okay, great. So far we have seen that this phase of instruction cycle can be decomposed into a sequence of elementary microoperations. For example, there is one sequence is for fetch, endeavor, and interrupt cycles, and for the execute cycle, there is one sequence of microoperation for each opcode. To complete the picture, I may give you another sequence of microoperations together, another examples about how to tie sequence of microoperation together, and this is done in the figure shown. Okay. Please pay attention to the figure on the right side. And we assume a new 2-bit register called the ICC instruction cycle code. Okay, here's the explanation. So the ICC designates the state of the processor in terms of which portion of the cycle it is in. 00 fetch, 01 for indirect, 10 for execute, and 11 for interrupt. At the end of each of the 4 cycles, the ICC is set appropriately, and the indirect cycle is always followed by the execute cycle. The interrupt cycle is always followed by the fetch cycle, and for both the fetch and execute cycle, the next cycle depends on the state of the system. Thus, the flow chart given defines the complete sequence of microoperations depending on the instruction sequence and interrupt pattern. Of course, this is a simplified example again. The flowchart for an actual processor would be much more complex. And in any case, we have reached the point of discussion in which the operation of the processor is defined as the performance of as a sequence of microoperations. We can now consider how the control unit cause the sequence occur. So as a result of our analysis in the preceding section, we have decomposed the behavior or functioning of the processor into elementary operations called micro operations. Yeah, I've explained in the first, at the first in this lesson. By reducing the operation of the processor to its most fundamental level, we are able to define exactly what it is that the control unit must cause to happen. Thus, we can define the functional requirements for the control unit, those functions that the control unit must perform. Okay, so the definition of this functional requirement is the basis for the design and implementation of the control unit. With the information at hand, the following 3-step process leads to characterization of the control unit. First, define the basic elements of the processor. Second, describe the micro operations that the processor performs. And third, determine the functions that a control unit must perform to cause the micro operations to be performed. And we have already performed steps 1 and 2, and let us summarize the results. Okay, so first, the basic function elements of the processor are the following: ALU, registers, internal data pads, external data pads, control unit. I will show you why this is already the complete list. ALU is a functional essence of the computer. Registers are used to store data internal to the processor, and some registers contain status information needed to manage instruction sequencing. Others contain data that go to or come from the ALU memory and I/O modules. Internal data paths are used to move data between register and between register and ALU. External data paths link register to memory and I/O modules, often by means of a system bus. And a control unit causes operation to happen within the processor. The execution of a program consists of operations involving these processor elements. As we have seen, these operations consist of a sequence of micro-operations. We should now see that all micro-operations fall into one of the following categories. The first category is transfer data from one register to another. Second category is transfer data from a register to an external interface like system bus, for example. The third is transfer data from an external interface to a register. And the fourth example is perform an ALU operation using registers for input and output. Okay, so being said, all of the micro operations needed to perform one instruction cycle, including all of the micro operations to execute every instruction in the instruction set, fall into one of these categories. We can now be somewhat more explicit about the way in which the control unit functions. The control unit performs two basic tasks. The first one is courtesy. The control unit causes the processor to step through a series of micro operations in the proper sequence based on the program being executed. The second task is execution, which is in this case the control unit causes its micro operation to be performed. The preceding is a functional description of what the control unit can do, and the key to how the control unit operates in the case of control signals, which we will discuss in next lesson. So that's for today. We have done. This is just a short explanation. Okay, we'll have much longer uh, class for next lesson. Okay, so here another a good inspiration, a good quote for you today. So Walt Disney once said, times and conditions change so rapidly that we must keep our aim constantly focused on the future. Okay, don't be uh, re- mourning about to be regret about our past. Okay, and not moving. Okay, we will lose many opportunities. Keep focused on the future. Okay, that's good. So thanks for watching. Here's what to do list. Subscribe, give a like, comment, and share this video to your friend. And my class will be on every Monday, and maybe not every Monday if I have certain occasion. Okay, but my class will be on every Monday if I'm not on some occasion that I will announce. Okay. Okay, so follow us too on social medias, and great to see you in this lesson, and see you on next lesson. Goodbye.